Thank you for the introduction. Hello, everybody. I'm opening the XR enablement track today, and I will be talking about the impact of visual experience on the enablement of such an important thing as immersion. The head-mounted displays are designed to create immersion, to make our brain work as if it would believe that that augmented or virtual world is real. One of the strongest means to achieve that is the presence. I put an HMD on, I'm there. I'm not here. I'm interacting with that world, not this world. However, simply being there is not yet enough to believe. There are factors that tell us why it's not real. One of the obvious ones is that feeling of the device on the head. Now, what about the visual experience? There is a mantra, seeing is believing. But is what we can see in head-mounted displays really telling us it is real or not? Imagine all the other factors causing the disbelief are eliminated. For example, you cannot feel the device on your head anymore. Would you believe seeing a blurry, smeared picture filled with false color stripes, the color fringing? Would you still believe if moving your gaze over the center, that fringing, that blur and that smear drastically increase? Well, if yes, then I believe you would be looking for a medical help. Such picture clarity and visual experience are scarily unreal. And those problems persist even in the latest and greatest devices, despite the growing pixel count. Actually, it even gets worse with the widening of the field of view, now moving your eyeballs, rotating your eyeballs to wide angles, you start seeing the geometry distortion, so-called pupil swim effect. The bottleneck is not in the pixel count. The bottleneck is in the optics that sits between the pixel array emitting the light and the retina absorbing the light. For an easier understanding, think of the entire system as of a digital camera, where the retina is the sensor and the rest is the lens. Well, first of all, in a head-mounted device, there is simply no room for a big, heavy, complex, high-quality optical system. The lens is constrained to be not much bigger, not much higher quality than something like a magnifying glass. And there is even a bigger problem. The eye pupil itself is a part of the optical system. It is a lens element that moves together with that retina sensor. It moves when you move your HMD on your head. It also moves when you simply rotate your eyeballs to look around. Think about that. In the digital camera manufacturing process, the lens barrel assembly tolerance is 3 microns. The eye pupil moves up to 8 millimeters in any direction. No optical design in the world can accommodate for such huge lens displacement. Those are fundamental optical problems having nothing to do with the pixel count. The pixel count alone doesn't work. The HTC Vive Pro is a good example of that. It has a substantially higher resolution than the original Vive. But it appears that the users do not see much of an improvement. In this slide, there is a quote from one of the first reviews of the Vive Pro. I'd like to draw your attention to the words, much of that extra resolution is useless. Well, the Vive Pro is not the highest resolution device nowadays, is it? Let's look at another one, Vario VR1, featuring so-called human eye resolution, which means the pixel count, the pixel density matches or exceeds the resolution capability of the retina. But does it really mean that the picture projected to the retina is so good, so we cannot see any better? We use this architectural drawing as a test picture for it having contrast edges and fine details. Closer view, and this is how it looks like in the Vario VR1. Look at those ranges. Look at that blur. Your eyes explicitly tell you this is not real. Despite the abundance of pixels, the visual clarity, the visual fidelity is poor because of those fundamental problems described earlier. Fundamental means irresolvable. So much irresolvable that it's even avoided to talk about that. Everyone just repeats those spells. The next generation HMDs are coming. 4K, 8K, 20 megapixel per eye. It looks like we are at the final, the fifth stage of grief, the acceptance of the loss of hope to achieve a realistic visual experience in virtual reality. It's so much accepted that the typical visual issue, those color fringes, are used as a marker of virtual reality. A couple of ads. You do not have to read the text to understand that's about extended reality. You can tell that from seeing those false color stripes. A conference logo, no need in those big VR, AR letters. Those color stripes speak for themselves. Well, a big news. Apple seeks to identify new AR, VR display technologies. Guess what? Of course. So desperate. Well, we at Almalence decided not to accept that the visual, that achieving a realistic visual experience in virtual reality is impossible. So let's dream. Let's imagine a hypothetical corrected lens system that improves the optical performance of the device and adjusts on the fly to the moving eye pupil position. And at the same time, adds no size, no weight, no mechanical complexity to the device, which means practically it doesn't physically exist. It works. Is that possible at all? Yes, but it's digital. We created a computational technology that characterizes the aberrations of an optical system. In other words, how a lens would spoil a picture in a way that it creates a transformation that is inverse to that aberration. Then applies it to the projected picture, to the displayed picture, so that the lens aberrations are compensated with that inverse aberration. Now, having a head-mounted display, getting the information from eye tracker, we know exactly where the eye pupil is located, so how exactly the optical system looks like at this very moment, and then getting the image data from the renderer, we can apply to that data an aberration that is inverse to the lens aberration. Once the picture gets projected, the lens aberration is canceled against that inverse aberration. The user sees high resolution, clean picture. We call it the digital lens, an algorithm by nature sizeless, weightless, flexible, and doing the job of a lens element. Let's see how well. This is a visible resolution map of the Vive Pro. The device is in the position, so the eyeball is at the optical axis. The top of the scale, 0.5 MTF, is the maximum possible visible resolution, so it's the displayed resolution. What we see here is that even in that very central area where we not consider the quality to be good, the user actually can see only about half of the maximum possible resolution. And then moving off the center, it quickly falls down to the quarter of possible, 10%, and even lower. Adding a corrective lens system, the digital lens, we dramatically enlarge that good quality area and push out the bad quality area. And what is really impressive and important, in the center, the resolution so drastically increases. So now the visible resolution matches the displayed resolution, the maximum possible resolution. Now the optics is not limiting us. Now it makes perfect sense to add more pixels, increase the pixel density. We will see more details then. This is how it looks actually. So Vive Pro as is, Vive Pro with a digital lens. I'm clicking back and forth. If you do not see a dramatic improvement, you just have to watch that at a larger screen. What happens if the device is not in the ideal position? For example, it slips down the face, say 3 millimeters. The visible resolution goes way lower. There are almost no points where the user would see any clear details. With the digital lens added, we make the displayed resolution apparent in a pretty large area, even bigger than the one in the ideal position, but without the corrective digital lens element. The color fringing, in the same case, the eyeball is 3 millimeters off the sweet spot. The color fringing is noticeable and annoying. With the digital lens, little to no color fringing at all gaze directions across the entire field of view. Let's get back to Vario. That's how it looked like. And this is with the digital lens. Without, with. Without, with. A closer look. Without, with. Without, with. I cannot stop doing that. Wow, look at that. Adding the digital lens to the existing devices, we dramatically increased the resolution and removed color fringing at all gaze directions across the entire field of view. Not only we harnessed the full potential of those devices' high pixel count, but we achieved visual experience improvement unachievable with the hardware design alone, which makes the digital lens an enabling technology, actually becoming indispensable with the gap between the increasing pixel count, the resolution, field of view on one side, and a fundamentally limited optical performance on the other side is increasing. The solution is lightning fast. We achieved about a quarter of millisecond latency on NVIDIA 2080 for the Vive Pro. The algorithm can run virtually on any computational gear, GPUs, vision processing units, etc. It can also be implemented in silicon and become a part of the display chip. With the digital lens technology ready for implementation, it is possible now that spell the next generation HMDs are coming will actually mean that we're going to see visual experience improved to the point where seeing will become believing. Thank you for your attention, and I'm very much looking forward to be able to meet you offline and show our live demo. Your questions are welcome.
Hey, welcome back. My name is Josh. I'm the track chair for the XR enablement track here at AWE Online. Here with Eugene from Almalence, who just gave us a great talk on his digital lens product and all of the great benefits of there. Eugene, how you doing?
Good. Hey, thank you for having me here.
Yeah, fantastic. That was really interesting. It sounds like this is something that your company is very, very passionate about, and you would. It sounds like Almalence is really dedicated to the development of this type of technology. I'm curious, what are the types of use cases that you're seeing the most uptake of digital lens? Like, what are, as it's being implemented, where do you see, what types of companies or what types of uses do you see being the most interested in it?
Okay, so well, basically, we are focused on the picture quality improvement, which can be useful everywhere. We thought that it's gonna be most demanded in some kind of industry applications, architectural design and stuff, where you really need to see fine details. Wherever high resolution displays, normal computer displays are used in the first place. But then talking to different people, it appeared like everyone wants that. We thought, for example, that gaming would be the last industry which would want that, because in the game everything is while moving really quick, you do not really care about the quality of that monster you're killing, but it appears that it's quite the opposite, because, for example, after killing the monster and getting some whatever money for that, you're choosing another weapon. And you want to see it in detail. It's like VR shopping, so to speak. So the gaming guys want that as well. So pretty much everywhere, to answer your question. It's like an evolution of the computer displays. You know, we had that VGA, whatever. My first display, I think, was like pure green and black, and then I had some 4 colors and stuff. And now we have 4K, 8K, and VR displays are now somewhere in the 80s. We need to move them, to push them to 21st century pretty quick in order for VR to take off. That's an evolution that is demanded by like everyone in the end.
Mm-hmm. Yeah, I can see that being useful for all sorts of applications, especially as headsets evolve and as advanced connectivity evolves. There's going to be this expectation of high fidelity rendering, and something like this seems like it would be really useful. I saw that you are the co-founder and the CEO of Almalence. Am I saying the name of the company correctly?
Yes.
What led you to co-found that company? Where did you see this? What was the aha moment where you thought the next generation of VR is on the way, and we can create something to help it get there and to be there when it arrives?
Okay, so actually VR is not something we founded a company for. We founded the company 15 years ago for the sake of development of computational image technologies, and mainly we've been focused on camera, and we still pretty much focused on camera. Like, we supply technologies to smartphone makers, and then like a couple of years ago we saw a possibility to apply our technology to the display pipeline in VR and AR, and to achieve a breakthrough that basically is not possible with a hardware design alone. So like a key component and an indispensable technology. And at that point we became like really excited. Like, we have a key for that industry to make some progress.
Yeah, that's pretty cool. It seems like you've been there, seeing where the trends are going, and you're really working to make sure that you're producing some really high quality value for where this technology is going to be in the next several years. So how can people?
Okay, now I can hear you again.
No problem. We're reaching the end of Q&A. I just want to know, how can people continue to ask questions, or how can people follow up with you after this session?
Okay. So drop me an email, contact me via AWXR, find me on LinkedIn. I'll type my email here in the chat, so just feel free to reach out. I'll be happy to answer any questions.
That sounds great. And that's been a really amazing talk by Eugene from Almalence, and thank you so much for hanging out with us today at AWE Online 2020.
Thank you. Bye.